Well, hi. Hope you guys are well. Everybody say hi to Jennifer.
Hi.
So, um, we are going to today talk a little bit about what to expect on your test tomorrow. We're going to do some review of our optimization techniques, and we're going to do either 2 or 3 example problems. Depending on how quickly we can get them done. With regard to your test tomorrow, you're going to be, yes, has been on your assignment sheet?
See, I'm not the only one.
Wow, you guys are off your feet here. Has been on your assignment sheet all week? Want to do a little look ahead, make sure that you get onto it? Really? Wow. Okay. So, also, I think I mentioned it yesterday as well. Okay. Well, what do you need to know? Really, we've done 3 things, and they all fall into the category of applications of derivatives. The first thing is graphing. And with regard to graphing, things like first d-test, second d-test, concavity, points of inflection, all the stuff that you did on your project. I could give you an equation for f that asks me to do some analysis. I could give you a graph of f prime and ask you to do some analysis, and so on.
What about motion?
Motion is an application of derivatives as well. If I do ask a question about motion, it will be in the context of graphing property. Okay? The second thing that we had were various applications of tangent lines. Estimation, Newton's method, and L'Hopital's rule. And the third thing, which we've been doing all this week, is optimization. And that's pretty much it. And you guys have taken enough of my test to know that basically they come out at about 3 pages most of the time. And hey, look, we've got 3 major topics. Gee. So there it is. Yes. Absolute max, the absolute maximum is exactly it. Speaking of, let's review. First of all, what is our goal when we are optimizing? The absolute maxes and mins. So in order to get there, I need to find what? Function, that's right. And once I find that function, I also need to establish its domain, that's right. Having established the function in its domain, now I have a choice of methods, either critical point endpoint, or argument from the sign of f prime. How does the critical point endpoint work?
Candidates.
Candidates? And do what with them?
Calculate it. Then,
Actually, F,
Or
F,
F,
F
but
is
you, yes, you're on the other
right, so what two types of candidates are there?
endpoints and critical.
And critical points, hence the name. Yep. How does the argument from the sign of F prime go? And find critical point, right? And do what with it?
As you see, it's greater than zero.
What's the tool of choice there? Yeah.
Well numbered.
Right, well labeled number one. And then we interpret that number line, and we're good. That's it. Okay, so that's how it goes. Now let's take a look at some specific examples. And I want to begin with your book, page 228, number 21. A rectangle is to be inscribed under the arch of the curve y equals 4 cosine 4π from x equals negative pi to x equals positive. What are the dimensions of the rectangle with largest area? And what is that area? Okay. Now the reason I wanted to focus on this question is first of all, it has a very important word here. Inscribed into the arch of the curve. And here's what that word means. If I were to graph y equals 4 cosine 0.5x from x equals negative pi to pi, then my graph would be the graph of a symmetric function that does something like this. And to be inscribed means that each of the vertices are going to be found on the boundary of the region. And in this particular case, if I draw my rectangle like so, then each vertex is going to be found on the boundary of the region, which consists of the curve y equals cosine 0.5x, and they implied in the x-axis. Okay? So that's what inscribed means. And as soon as I draw this, now I start labeling. And in particular, since I don't know the x-coordinate here, I can call it x. And as soon as I call it x, the other guy has to be the opposite of x, because my curve is symmetric about the y-axis. And as soon as I call this point x, its y-coordinate is constrained by the fact that it must be on the curve. So that the y-coordinate is 4 cosine 0.5x. And this y-coordinate is also the same. So that to be inscribed under the curve means that the vertices are going to be on the curve, which means that they are going to have coordinates x comma y, where y is defined by the bounding curve. Now, the rest of it's pretty straightforward. I am looking for a rectangle with largest area, and so I need an area function. And since I'm looking at a rectangle, my shape is exactly, very good. This length is x, this length is x, y here, like so. And so the area is going to be length times width. And furthermore, since y is known, I can immediately replace this. Replace y with what it is. So this gives me a perfectly legitimate area function. Next question, domain. The smallest value of x is pretty clearly 0. There was an interesting discussion in the other class. Could I let x actually become negative? I could actually do that, but when I do, I sort of flip the rectangle inside out, and I end up with another rectangle identical to the previous one. So the feasible domain here is really from 0 out to the largest possible value of x, which is pi. And visualizing it, it seems pretty clear that if x is 0 or close to it, my rectangle will have 0 area. And if x is pi or close to it, my rectangle will have 0 area. And somewhere in between is the max. So that suggests that a critical, argument from the sign of a prime is probably a good idea. All right, so I need a critical point, and I compute a prime using my product rule. First times the derivative of the second. Don't forget outside and inside. Plus the second times the derivative of the first. We can do a little bit of cleanup because we have 8 times negative 1 times a half is negative 4. And now we set a prime equal to 0. Now the first reason that I wanted to do this problem was to talk about the word inscribed. The second reason I wanted to do this problem is because of this equation right here. Does everybody see that this equation contains a combination of trigonometric functions and polynomial functions? Because of that, it is algebraically impossible to get an exact algebraic solution. I have to use the calculator to solve this equation. So, everybody get your calculators out and go ahead and solve this equation right here. You know what? I could do this on the calculator myself here. Make sure that you are in radian mode, especially if you're in physics. Otherwise your calculator will be confused. Give you no solution probably.
Yeah, I use well labeled number line like the second message to solve it's kind of pretty good to write the zero.
In other words, if you've already decided you're gonna use argument from A prime, do you have to worry about domain? Yes, you do wanna worry about domain, because that domain will also control which critical points that you find are legitimate. You're not gonna accept critical points outside the domain. Oh, let's see here, it's negative 4x sine 0.5x
Yeah.
plus 8 cosine 0.5x. Mode is radians, window size 0 to pi, let's make that 4, and probably do. That's a nice graph. And so you should have ended up with a graph like this, and when we do second calc 0, left bound at 0, right bound at, we can estimate that at 3, and I guess it may be 2, and we get 1.7207. Now here is an added benefit of having solved on the calculator, because from the graph I can directly see the signs of A prime. A prime is positive over here, and it's negative right there, and I can fill out my number line on that basis. Isn't that nice?
I don't know if you use color more.
There will be some problems, yes, some no. Yes.
Oh, I did the different but only differentiable correct.
See what you have for your Y1?
So,
Oh, I see, you found the intersection point of the two terms. Yeah.
but how can I get a prime from this graph?
That's harder. If you're gonna be clever, then you're gonna have to be clever. What would you say? If this guy right here, what he did was he subtracted this term from both sides and then found out where these two terms intersected each other. Okay. So how would you tell whether your derivative is positive or negative?
No,
There is. How about this? Won't the derivative be positive when this term is bigger than that term? And that occurs whenever the graph of this guy is above the graph of that guy. So if you could see your two intersecting graphs right there, and this one is y equals negative 4x sine 0.5x, and this one is y equals negative 8 cosine 0.5x. And you can see that over here, this curve is above that one, hence this curve will overwhelm that one and make your derivative positive. But why be so clever?
so I don't know how to do that. I didn't,
Oh,
I couldn't do that.
so what you're missing then is the 0 finally. Second calc 0. And that will let you find the intersection of the x-axis. Or alternatively, you could set y2 equal to 0 and find out where those two intersect. Okay, so all we need to do now is to write our number line in words. Clear? You got this? Uh-huh. Good. And that's the reading of the number line. So now you want to draw your conclusion that area of 1.7207 is x. Okay. Now we need to make sure we've answered the question, because the question was not what is x. The question was what are the dimensions, excuse me, of that rectangle, and what is its area. And the dimensions are 2x times y. So, I have to say that the dimensions are going to be 2 times x. And I'm just a little bit lazy about it if I'm working on a test, right? I'm just going to write it like that. And I'm going to say that the height is going to be so, and those are perfectly good numbers. And the area is equal to 8 times 1.7207 is the cosine of half of 1.727. I'm not sure whether it's properly lazy to work that hard to avoid evaluating. Who knows? But that's probably how I would do it. Yes. That was our answer. Over the height. Well, our y,
Isn't it 0.5 times that?
yeah, 0.5, that is 1.727.
Oh,
Times minus.
Oh, not minus, times. Yep.
So, how do that in this program?
Yeah, absolutely, sure. Yes, critical point input? Yeah, sure. Mhm. But here, because my graph so clearly gives me the signs, okay, this thing's not behaving. Because my graph, which looks like this, so clearly gives me the signs of f prime, it makes a whole lot of sense to just use that graph right. See what I'm saying? All right, I'd like to change gears and take a look at number 36, which is a very different problem. Find the volume of the largest cone that can be inscribed in a sphere of radius. I'm not sure that it's put exactly like that, but we're going to do that, and we're going to express it in this way. Now, I want to do a little sidebar on solids, because I found in my other class that there were some geometrical formulas that some of them did remember and some of them did not. There are 3 basic shapes that keep on showing up over and over again in mathematical work. One of them is the cylinder, which takes a base and replicates it straight up like so. And the volume of that cylinder is going to be the area of the base times its height, like that. If my cylinder happens to be circular, then that would be pi r squared. And the surface area of that cylinder is going to be formed by taking the 2 end caps and adding to that the lateral area, which is the perimeter times the height. Think of splitting this open and unrolling it so that you get a rectangle that has a length of the perimeter and the height of each. So that's the cylinder. And we did that with the can problem, remember? Except our can had an open top, so we only added 1 base to it. The second type of shape that shows up a whole lot is a cone or a pyramid. And with a cone or a pyramid, you have a base, but now the whole thing comes to a point. And the volume, therefore, is 1/3 of the volume of the corresponding cylinder. And we can actually prove that formula with calculus, but we'll just leave it as it is for now. If I happen to have a circular cone, then the surface area can be found by adding base to the lateral area. And the lateral area is kind of interesting. It has a value of pi times the slant height times the height of the cone. Excuse me, times the radius of the cone for a circular cone. And the final technical shape that we encounter is a sphere, radius r, and the sphere has a volume of 4/3 pi r cubed and a surface area of 4 pi r squared. And it's interesting to note, and not a coincidence, that the derivative of the volume formula is exactly the surface area formula for the sphere. So if you did not remember these from geometry, these are totally worth knowing. We're actually going to derive some of these formulas when we get to integration.
Is it pi, 4/2 pi squared?
4/3 pi r cubed. Right? It has to be cubic units.
For the pyramid, for surface area.
This would be for the circular cone only. E plus that. What this measures is the lateral area right here. And the way that you get that basically is by slitting right here and flattening it out. And when you do, you get a circular section. Okay. Now, let's consider what this problem is asking of us. We have a sphere, and inside that sphere, we are going to inscribe a cone. Now, we've seen that word inscribe. That means that all of the extreme points on the cone are going to make contact with the sphere. In particular, the entire bottom circumference and the vertex are going to lie on the sphere. Here's the center of my sphere, and that sphere has a radius of r. And what I'm going to try to do now is to find the volume of the largest possible cone here. So I need a function for that, and since it is a cone, then I write the volume as 1/3 pi r squared h, where r is the radius of the cone. Don't confuse that with big R, the radius of the sphere. And h is the height of the cone, which goes all the way from the center up to the vertex of that. Now, here's the problem, of course, and that is that I have two variables. And those two variables are going to be related to each other because my cone is physically constrained by the sphere. How do I express that in net? Well, I need to go do some geometry on this stuff. The first thing to observe is that in a sphere, everywhere you go, there's a radius. In other words, if I draw from here to here, this length is necessarily big R. And the second thing to observe is that the center of the sphere divides the height h up into two pieces. And the first piece is r, and the second piece is therefore h minus r. Let me do that in red so it's a little clearer. From here to here is h minus r. Now, if you see what I see is a right triangle. And this right triangle has a hypotenuse of big R. It has a height of h minus big R. And it has a leg of R. And so therefore I can immediately write that big R squared equals little r squared plus h minus big R squared. And that is the constraint that comes about from inscribing the cone inside the sphere we're reducing. This could seem a little simplifying, so I'm going to h squared minus 2hr plus r squared, and I get a bonus. Who sees what wonderful algebraic thing can happen here? Yes. The big R squareds go away, which is nice. And that allows me to say that little r squared is equal to, add and subtract, 2hr minus h squared. Okay. How does that help me? Well, remember that my volume formula was 1/3 pi r squared h, right? And look, I just found r squared. Yes.
So we have another variable for it.
Ah, the big R is not actually a variable. It is the radius of the sphere, and my answer will be in terms of big R. Right. So I can replace the r squared here with what I found from my constraint, which is 2hr minus h squared times h. And we like that. That's nice. Let's clean up by distributing. And now we have a volume in terms of height h. What about the domain? Well, the smallest possible height that I could have would be h equals 0. That would be a weird cone right there. And the largest I can have would be h equals 2r. So I'm ready to find my critical points. dVdh equals 4/3 pi r times h minus 3/3 pi h squared. Set that derivative equal to 0 and solve by factoring. And in fact, it makes a whole lot of sense to factor in pi as well, right? So that either h is equal to 0, that's a critical point at the end of the domain right there. Pretty obvious, if h is 0, it corresponds to a volume of 0. That's a minimum. Or h is equal to 4/3 r. Let's come back and see if that makes any sense. Oh yeah, it does. H equals 4/3 r means that h would be just a little bit larger than the radius down here. That makes a lot of sense. But we can verify it. If I take, for example, h is equal to r, and I plug into the derivative here, then I get a positive value. And if I take h is equal to 2r, then I'm going to get a negative value, so that v of 4/3 r is max. Well, if the height is 4/3 r, what is the radius? Remember that r squared is equal to 2rh minus h squared, which is going to give me 8/3 r squared minus 16/9 r squared. That's kind of empty, but that would be 24 over 9. 24 minus 16 is 8. And that's equal to little r squared. So little r is equal to root 8 over 3 times big R. Yes?
And last time you said if we have more than 2 critical points, we can use not use the argument.
Yeah, that's true. That critical point was just outside our domain. Isn't that interesting?
Wait, what is a 0
To 2R,
close?
open. Well, because having h equals 0 would mean I didn't make home.
Yeah. If,
But even if I took it as a closed domain, still, from 0 to 4/3 R, my function's increasing and then decreasing, right? So there's only one option, that's the max.
because of 0 is not.
Yeah. So this problem was interesting to us, first of all, because it was a little bit abstract, right? Second of all, because we dealt with the inscribed notion right here with an equation that corresponded to the fact that my cone has to fit inside the sphere. So this equation said in math what our diagram said geometrically. Does that make sense? There was a correspondence between the geometry and the algebra. And that was the main thing that I wanted to get across. Questions on this one? Let's take a look at one more, number 41. In number 41, we have a curve y equals square root of x. And we have a point 3/2, 0. It's on the x-axis. And the question asks us is, what point on the curve y equals root x is closest to the point 3/2, 0. So this is a really interesting question. We don't know where the answer is. It looks like it'd be about here, right? And we can label that point as x comma square root of x, much like we did for our inscribed triangle here. But now what we need is a function, and the function that we are trying to minimize closest to means minimum distance. Closest to means minimum distance. Exactly. This distance right here. Now, do you remember the distance formula? Vaguely. Do you remember the Pythagorean theorem? Ah, well, the distance formula is just the Pythagorean theorem. If I go down to this point right here, this point has coordinates x comma 0. And so this leg right here is going to be x minus 3/2, or 3/2 minus x. And this leg right here is going to be root x minus 0. So I can say that the distance squared right here is equal to the difference in x's squared plus the difference in y's squared. Now here's the interesting thing. I'm trying to minimize distance. It turns out that if I minimize distance squared, I will get the exact same point, but I don't have to worry about any square roots. So, to minimize distance, the indicated procedure is to minimize the square of the distance. Not that those two are exactly the same. Minimize the square of the distance. Not that those two are exactly the same, but the solution to this problem will be the same as the solution to that problem. Yes? Who wants it? Maybe not. So let's call this function f of x or something like that with the distance squared. And I agree with both Tony and Jason's suggestion, let's do a little bit of simplifying, because it sure looks to me like we could get a lot of leverage.
I think that's X.
Oh, you're right, this is X. We could get a lot of leverage by simplifying our distance.
Square.
Now we take a derivative, set that equal to 0, and we have a delightfully simple solution, x equals 1. And going back to here, that looks about right where our guess was. And if we consider now the well-labeled number line for f prime at x equals 1, if we consider maybe plugging in x equals 0, and we consider maybe plugging in x equals 2, and it's fairly clear that our number line looks like this. And therefore we say we have a minimum distance at the point x equals 1. What is y equal? Also 1, because y is equal to the square root of x. And we're done. Isn't that nice?
So we don't have to write ground terminal X is less than 0 or
Oh yes, that's a good point. I should write the justifying language, shouldn't I? Yes. Tony, give it to us.
that terminal X is less than 0 when X is less than 1. That term is greater than 0 X.
That's it. And all that he's doing is showing that he can read the number line. Very good. Okay. I will see you guys tomorrow. Bright and shiny faces all studied up. And everything. How many midterm exams do you have?